C. Now look at this. ABC is equal to AC for all ABC in S. So just it's a product of last two elements. It's product of last two elements. ABC is equal to AC. So here A, then CB, then C. So it's also the product of last two elements. It's equal to AC by our given condition. AC. What's AC? AC is X. So therefore L is a left to zero semigroup. Therefore L is a left to zero semigroup. Similarly we show that similarly we can see that R is a right zero semigroup. R is a right zero semigroup. So L is a left to zero, R is a right zero semigroup. Now I will show that S is isomorphic to L cross R. S is isomorphic to L cross R. Now we show that S is isomorphic to L cross R. So let's define a map from S to L cross R. Define psi from S to L cross R by X psi is equal to XC comma CX. So XC is an element of L because X is an element of here X is an element of S. So XC is an element of L, obviously, because what's L actually? L is equal to SC, R is equal to CS. So elements of L are elements of S times C. So X is an element of S, so XC is in L. And elements of R are the C times the elements of S. C times the element of S. X is in S. X belongs to S. So it's in L cross R. Now we show that it's 1 1 on 2. This map is 1 1 and on 2. So let's prove its first 1 1ness. Phi is 1 1. Psi is 1 1. So choose any 2 points. Let X, Y belongs to S such that X psi is equal to Y psi, which is true if this XC CX is same as YC and CY. So which implies XC is equal to YC and CX is equal to CY. We have to show that X is equal to Y. We have to show that X is equal to Y. So we have this X now. Now X, since every element is an idempotent, so X can be written as X square. X is same as X square. And this X square is same as XCX because the product ABC is equal to AC. Product of last two elements. Okay. And XCX. What's XC? It's YC. Actually, it's XC is YC. It's equal to YCX. Okay, it's YCX. And this CX is CY actually. CX is CY here, you can see. So XC is YC. XC, this one, XC, it's equal to YC. X is here. Then we have CX. What's CX? CX is CY. So Y times CY. And this is equal to Y square, which is equal to Y because every element is an idempotent. Y square equal to Y. Thus X equal to Y. Thus X is equal to Y. So therefore this psi is 1 1. Psi is 1 1. So next we show that this psi is onto. Second property, psi is onto. So let's choose any element in L cross R. So let us suppose that elements of L is like this AC, L elements of R is like CB. Suppose it belongs to L cross R. L cross R. Okay. So now AC CB is equal to it's equal to AC is equal to ABC. It's equal to ABC. Okay. And CB is equal to CAB. It's equal to CAB. It's equal to okay. And this one, it's equal to now here ABC into C times AB, and that's equal to AB psi. You can easily verify it. It's a definition of psi actually. What's psi here? X psi is equal to XC CX. XC CX. So here it's psi of AB. It's equal to ABC. Instead of X we have AB here. ABC and C times AB. So that means for any element AC, CB in L cross R, there is an element AB in S, where this AB it belongs to S. Thus for all AC, CB in L cross R, there exists an element AB in S, such that psi AB is equal to AC, CB. So that implies psi is on. Now the final property, psi is morphism. Psi is morphism. So again I have to choose two elements from S. So let S comma Y belongs to S. Then I have to find X, Y, psi. It should be equal to X psi, Y psi. By definition, it's equal to X, Y, C and C, X, Y. By definition of psi. So this one, this X, Y, psi, it's equal to this X, Y, C is equal to X, C, and C, X, Y is equal to, it's just equal to C, Y. So because the product ABC is equal to AC, XYC is equal to XC, CXY is equal to CY. So it's equal to here, it's equal to XYC is XC and CY is CY. It is CY. Okay. Now this can be written as XCYX, XCYC, because again the product of XCYC is the product of last two elements. So treating this CY as the middle element, so it's equal to XC, and here I write it C times I will write here C times XC Y. Okay, this one. Okay. Now since it's L cross R is a semigroup with respect to the component wise operation, so it's equal to XC comma CX into YC comma CY, and that's equal to X psi and that's equal to Y psi. So that means psi is, therefore psi is an isomorphism, therefore psi is an isomorphism, and hence S is isomorphic to L cross R. So now we prove third implies 4. So what's third? Third means that this psi is isomorphic to S is isomorphic to this. Assume S is isomorphic to L cross R, where L is left zero semigroup and R is a right zero semigroup. Right zero. So assume third holds. Third means S is isomorphic to product of left zero and right zero semigroup. So L is left zero and R is right zero semigroup. We need to show that this. So we can write also equality here instead of isomorphic because they are one and the same thing. So let's replace this. We can treat this L. Treating this L as A, and taking L is equal to A. So I want the property number 4 actually from property 3. So take A is equal to L and B is equal to R, because I need to show that it's just the property number 4th. I need property number 4. What's property number 4? It's this. This is the property number 4. I need to show that S is isomorphic of the product A cross B, where A and B are non-empty sets with multiplication is given by this. So then A cross B is a semigroup. It's a semigroup because L cross R is a semigroup. Also, if I choose any two elements from A cross B, also let A1 B1 comma A2 B2 belongs to A cross B. I need to prove this property. It is a semigroup such that for any two elements the product of A cross B is given by, for any two elements A1 B1 and A2 B2 in A cross B, A1 B1 into A2 B2 is equal to A1 B2. So let's check this. Then this product A1 B1 cross A2 B2, not I don't write here cross, it is just the multiplication, simple multiplication notation. So this is equal to, this product is equal to, this product is equal to and this is equal to, it's just component wise multiplication here, it's equal to A1 A2 B1 B2, but A is actually L, it's a left to 0 semigroup, so A1 A2 is equal to A1 and this B is equal to R and the other elements are B and B is a right 0 semigroup, therefore B1 B2 is equal to B2. So that proves this result. The product A1 B1 into A2 B2 is equal to A1 B2, and here A1 B1 into A2 B2 is equal to A1 B2. So that proves that third implies fourth. Now we prove last property, fourth implies first. So let S be equal to A cross B such that for all A1 B1 comma A2 B2 belongs to, it's actually isomorphic, so we can treat they are equal also without loss of generality. Then this A1 B1 into A2 B2, it's by definition it's equal to A1 B2. Now we show that this S is a rectangular band. That means ABA. We need to prove first property. What's first property? First property is this: S is a rectangular band. S is a rectangular band means ABA is equal to A. So now that means for any two elements A1 B1 A2 B2, the product A1 B1 into A2 B2, we have to check this. Let's treat this as A and this treat this as B. Okay, we have to show that ABA it should be equal to A. What's A is A1 B1 into BB is A2 B2 into A is A1 B1. That's equal to this one A1 B1. It's equal to A1 B2 by definition. A1 B2 into A1 B1. Again, it's the first element of this and the second element of this one, that's B1, which is equal to A. So that means ABA is equal to A, so which means that S is a rectangular band. So thus S is a rectangular band. So this proves this theorem completely. Thank you.